This is section 5.5 on average value. Our goals are to derive the average value of an integrable function and use in practice, and state the mean value theorem for integrals and use it as well. As our class opener, first I'd like to compare the following things. The integral from a to b of f of x dx and the integral from b to a of f of x dx. Those two would both have the same area if you took the absolute value, but when you go in this direction from b to a, it changes the sign of that area if you change the direction from b to a to b. Right? So, also, this may not be clear yet, but once you see it and you figure it out, well, it would make total sense. But the integral from a to a of f of x, there would be no width to that interval, and therefore the area beneath that curve would have to be 0. Alright, let's talk average value. How would we find the average of a set of numbers? Well, we'd take the sum of that set of numbers and divide by the number of numbers. But what if the set of numbers is infinite? Well, then we'd consider f of x on an interval. And the definition of the average value is just, this is notation for average value. Find the area under the curve and divide by 1 over the length. This is the length of the interval. Okay, so if I took the integral of this function f of x dx and I multiplied it by 1 over 5 minus 0, I would get a value. Right? I take 1/5 of the area under the curve, and it looks like that would be equal to 4,000 in this case. All right, so that's the average elevation in this specific scenario along a 5-mile stretch on a path. Now, I wasn't going to go through the formalities of integrating that because I didn't really want to, and I didn't really need to in this case because I was given that nice average elevation there at 4,000. Alright, so the mean value theorem, why is this all cockeyed? Let me move this a little bit. There we go, that's better. So the mean value theorem for integrals just says that a continuous function always assumes its average value at least once on the interval. So it actually could hit that average value multiple times. Right? This mean value theorem is let f be continuous on the interval a to b. There exists a point c such that some f of some value equals that average value. So to me it looks like that that value c here would be 3. So the algebraic way to do this would be to take f of x, which from the last page was the following. And what you want to do is you want to set it equal to 4,000. This is going to be an ugly situation, but subtract 4,000 and then solve, either using your calculator, factoring, quadratic formula, whatever is necessary in that given situation. Alright, so let's do an example of average value. So now our function is 1 over x. So recall that the average value is equal to 1 over b minus a, Well, b is e and a is 1. Right? There's a, there's b. Alright, times the integral from 1 to e of 1 over x dx. So the average value of f will equal 1 over e minus 1 times the natural log of e minus the natural log of 1. Okay, recall that the integral of 1 over x is the natural log of x. Alright, so that will equal, let's see, what is this? Natural log of 1 is 0, natural log of e is 1. Therefore, it looks like our average value is going to be 1 over e minus 1 times 1. And that's e. Okay, so on this question here, it says find the average rate of change of this function. Okay, so basically what it's asking for is the average value of f prime. Okay, average rate of change of this function. It's asking for the average value of f prime. So the first thing we need to do is find f prime. This is going to be fundamental theorem of calculus, right? Part 2. So the average, or the derivative of that function would be 1 square root of 1 plus cosine. We directly input this x squared. The derivative of x is 1, therefore chain rule is not necessary. And now what we're going to do is we're going to find the average value by taking 1 over b minus a. There's b, there's a, so 3 minus 1 is 2. Of the integral from 1 to 3 of f prime of x. Okay, you're going to need a calculator for that one. And my calculator spits out 0.858. Alright, let's find the average value of cosine x on the interval from -3 to 5. So 5 minus -3 is going to be 8. So I want to take 1/8 of the integral from -3 to 5 of cosine of x dx. So my average value would be 1/8 of the integral of cosine is sine. So it'd be sine of 5 minus sine of -3. Now we're going to want to be careful here. Since sine is an odd function, sine of -3 is actually equal to negative sine of 3. Okay, because it's an odd function. Therefore, this negative and this negative will make a positive. So I'll have 1/8 sine of 5 plus sine of 8. Oops, I'm sorry, plus sine of 3. So I think, where do we got that? Well, these are all out. That's divided by 2. Looks like E is our answer. Alright, the velocity in feet per second of a particle moving along the x-axis is given by that. What is the average velocity of the particle from time t equals 0 to time t equals 3? Alright, so we're going to use our calculator here. This function right here, as you look at it, just looks like it would require that. Plus we're told calculator allowed. This is A, this is B. So the average value or average velocity on this function from 0 to 3 would be 1 over 3 minus 0, which is 3, times the integral from from 0 to 3 of e to the t plus t e to the t dt. And if you use your calculator correctly, Math 9 That's the way. Math 9. And then divide by 3, you'd get 20.086 feet per second. Alright, calculator allowed again. A plane flies in a straight line with positive velocity in miles per minute at time t minutes, as shown above, where v is differentiable function of t. Selected values of v of t for 0 to 40 are shown in the table above. The function f, defined by f of t equals that, is used to model the velocity of the plane in miles per minute. According to this model, what is the acceleration of the plane at t equals 23? Okay, so for part C, it's been a while since we just talked acceleration, but what we would do is if this function here models the velocity, then we would want the derivative of that function evaluated at t equals 23. Our units of measure in a moment here, if that is miles per minute, we would have miles per minute squared. Alright, let's evaluate on the calculator. Okay, so f prime of 23 on my calculator gives me approximately negative 0.407 miles per minute per minute. Okay, so according to this model, according to f of t right here, what would be the average velocity? So the average velocity would be over the interval 0 to 40 would be 1 over 40 times the integral from 0 to 40 of that function, 6 plus cosine of t over 10. Clearly need a calculator on this one. That would be a headache dt. Okay, so I'm going to evaluate on the calculator and see what we get. The value I'm getting is 0.798 miles per minute. Okay, so whoops, I caught myself. That should be a 40, not a 4. That changed my answer entirely. It's a good lesson to learn. Look at your values, right? If I look at these values right here, 0.798 does not look like a good average there. When I redid my answer and worked with the 40 instead of 4 there as my upper limit, I got 5.916 miles per minute, which makes a lot more sense. Okay, so in this case up here, I'm doing a derivative, so I'm going to use Math 8. I'm just evaluating a derivative numerically. And down here, I used Math 9, just to be aware. That's your numerical derivative, Math 8, and your numerical integral, Math 9. Alright, that'll be it for today. Average value, 5.6? Nope, 5.5. The average value and its properties. Have a great day. See you next time. Alright, one more question here.